sometimes we might want to ask a microservice to do something that we don't need to wait for. A good example in the eShop on Containers website would be the process of submitting an order. When we submit an order, there might be all kinds of tasks that need to be done by the back-end systems, including taking payments from a payment provider, maybe ordering additional stock from a supplier, and then initiating the shipping process from the warehouse. And this process might take a few days to complete, and so we can't expect the user of the website to wait all that time to get an order confirmation. They just need to know that their order has been accepted, and they can come back later to check its progress. We might even send them email updates to keep them updated on their order status and let them know once it's out for delivery. And we can achieve this by making use of asynchronous communication patterns. It is possible to implement asynchronous communication patterns over HTTP. For example, when a customer submits a new order, our ordering microservice could return a 202 accepted HTTP response code rather than a regular HTTP 200 OK response code. 202 means that you've accepted a request to do some work, but you haven't carried it out yet. And in the response body, you often send an ID of some sort, so that the client can then poll for the status of that work to find out if it's completed. In our example, that ID might just be the order number. You might also want to combine this technique with the use of webhooks, where the microservice itself reports back when it's completed the task. In this model, when a client calls your microservice, they can register a callback URL on which they'd like to receive any notifications. But another very common pattern for asynchronous communications is for microservices to publish messages to an event bus. Rather than directly calling the other microservices, they simply create a message and send it to a message broker, which serves as an intermediary. Other microservices then subscribe to those messages. And this pattern has a number of advantages. First of all, it completely decouples the microservices from each other. So instead of one service directly calling the next service, instead it simply talks to the message broker. This means that if the second service is temporarily unavailable, then the first service is still able to function, and the second service can just process any queued up messages once it's online again. This approach is also very beneficial for supporting more advanced scaling patterns. If the number of unprocessed messages for a microservice is building up, you can scale that microservice out to multiple instances to help work through the backlog of messages quickly. And many serverless hosting platforms do this automatically for you. But with containerized solutions, it's also possible to achieve the same thing by configuring some automatic scaling rules for the cluster of virtual machines that your containers are running on. There are several different types of messages that you can use. Two of the most important types of message are commands and events. A command message is a request for a particular action to be performed. You can think of a command message as saying, "Do this, please." Imagine you have a microservice that sends out emails. That doesn't necessarily need to work synchronously, so it's a good fit for asynchronous patterns. We could post a command message that specified the details of the email that should be sent, and the email microservice could pick that up and send the message. Maybe the email microservice could get a bit behind if we posted large numbers of these command messages to its queue, but it would eventually catch up. The other type of message is an event. An event message is simply a way of announcing that something has happened. Events are in the past tense and are not directed at any one microservice in particular. When you publish events, you're allowing any other microservices in your system that are interested to subscribe to that event and perform their own custom actions when it occurs. For example, if there was an order placed event in an e-commerce system like eShop on Containers, then several actions might need to occur as a result of that event. For example, charging your credit card, sending a confirmation email, or checking on stock levels. And so each microservice that needs to perform an action when an order is placed will be triggered by that single event being posted to the event bus. And if you're interested in learning more about messaging patterns, then a great book to look at is called Enterprise Integration Patterns. And there are also several practical courses here on Pluralsight that will show you how to implement those patterns using various message brokers, such as RabbitMQ or Azure Service Bus. So do check those out if you're interested in learning more about messaging. We can't assume in a distributed system that all the microservices will be up and running the whole time. We can't even assume that the network is going to be reliable. So we must expect from time to time that communication from service to service will fail due to transient issues. And it's very important that we handle these failures well, as they can result in cascading failures that are very difficult to recover from. And there are several techniques and patterns that we can apply to increase the resilience of our service-to-service communication. I'll just mention a few of them. If you're making any kind of network call, such as a regular HTTP request to another service, or maybe making a query to a database, then it's a great idea to build in retries with backoff. This means that if your first attempt fails, then you just wait a few seconds and try again. And if that fails, then you wait a bit longer and make another attempt. And this simple technique can often be all that's necessary to handle various transient service outages. And you might find that your programming framework of choice has got built-in support for this functionality. For example, in .NET, there's a great library called Polly that makes this very easy to implement. However, if too many retries are attempted, you can end up making the situation worse, and potentially you end up effectively issuing a denial of service attack on your downstream services because you're calling them so frequently. And so another pattern that can help us with this is called a circuit breaker. A circuit breaker sits in between the client and the server, and initially it allows all calls through. And we call this being in the closed state. However, if it detects any errors, maybe the server is returning error codes or it isn't responding at all, then the circuit breaker opens, which means now, whenever the client makes a call, it's going to fail fast, rather than passing on that request to the server. But after a configured timeout has elapsed, the circuit breaker allows a few calls through again to see if the downstream service has recovered. If so, then the circuit breaker closes and it allows all calls through again. If the downstream service hasn't recovered, then it remains in the open state a bit longer, again quickly rejecting any incoming requests. And this is a very simple but powerful technique, and again, many programming frameworks will have ready-made implementations of a circuit breaker that you can take advantage of. Caching can also be a valuable part of a resilience strategy. If you cache the data that you receive from a downstream service, then if that service is unavailable for a short period, you might be able to fall back to the data in your cache. Of course, that assumes that you have thought about the implications of using stale data. One of the reasons message brokers are so popular in microservice architectures is that they have inherent support for resilience. We can post messages to the message broker, and it doesn't matter if our downstream services are not currently online. When they start up again, they can catch up on the backlog of messages that are waiting for them. Message brokers also often support the ability to retry sending a message. If a message handler fails for any reason, the message can be returned to the message broker to be redelivered later. And this effectively means that you get a certain number of retries for free simply by using messaging patterns. Of course, you don't want to get stuck in an infinite loop, attempting to process the same message again and again. So usually after a certain number of retries, the message broker will consider this message to be poisoned and put it into a dead letter queue. Now, there are some challenges associated with messaging that you do need to consider. One is it's very hard to guarantee that messages will always be received in order. So you need to take care that your message handlers will do the right thing even if they receive messages out of order. It's also possible to receive a message more than once. One example of when this can happen is when you receive a message for the first time, maybe you only got partway through handling it and something went wrong, and so the message got returned to the queue. And now later, you receive that same message again as a retry. And this scenario is why it's really important to ensure that your message handlers are idempotent. A message handler is idempotent if calling it twice with the same message has essentially the same effect as calling it once. A good example in our e-commerce sample application would be handling an order. We only want to charge your credit card once, and we only want to ship your order once. So if the order received message gets processed twice for whatever reason, we need to make sure that we've got good checks in place in our code to protect us from charging you twice or shipping your order twice.